All right, so let's get started here. We're going to pick up where we left off last time, but actually first I want everybody to take a second and name this compound here for me, okay? Because what we're going to do is we're going to add one more thing to our notes here. We talked about our nomenclature of these conjugated dienes, how we have to retain that A because we're going to use that di prefix. All right, but there's another important thing about finding our parent chain that I want you all to have in your notes here. Your parent chain is, again, that longest continuous set of carbons. All right, with this important caveat, now that there's this functional group in our molecule, is that that parent chain must contain that functional group. Right, so the parent chain has to contain that carbon-carbon double bond. Okay, so everybody take a second and then name this molecule for me, keeping that rule in mind here. All right, so my whole point of this example here is that yes, these 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons are the longest set of carbons, but this does not contain that functional group. It does not contain that carbon-carbon double bond. So this is not the parent chain of my molecule. Right off the bat, I know that those 2 carbons must be in the parent chain of my molecule. All right, so in this case, it's symmetric, so it doesn't matter which direction I want to go. I'm going to say it's those, what is that, 2, 4, 6 carbons right there, which means that this is just a substituent. 4 carbon substituent, so we would call it a butyl group. Okay, I'm going to number my parent chain. I'm not even going to look at that butyl group, right? I'm only going to make sure that my double bond gets the lowest possible number. So that means I need to number in this direction here. So my name for this molecule would be 2-butyl 1-hexene. All right, so again, our parent chain must contain that functional group. Okay. Let's review what we talked about last class here. We have these electrophilic additions of conjugated dienes. These are additions of these electrophiles. Gosh, sorry. Really trying to sneeze, but it's not going to happen, so apologize. Anyways, we got these 2 possible products, our 1,2 adduct, where we add that HBr to our double bond. The bromine is always going to go in that allylic position. And this would just be kind of our normal old addition reaction. We also have a second product as a result of resonance, our 1,4 adduct. And where we left off last time was the idea that we can control which one is going to be our major product by adjusting the temperature of our reaction mixture. At low temperatures, this favors the 1,2 adduct. And at high temperatures, this favors the 1,4 adduct. All right, and we're like, okay, well, what the heck's going on here? So what we did was we looked at a free energy diagram of this reaction here. First, we looked at just a regular free energy diagram. We noted that by paying attention to the endpoints, we get information about the thermodynamics of this reaction, right? Which one is, the delta G of our reaction. And by paying attention to that activation energy barrier, we get an idea about the kinetics of our reaction, how fast that reaction goes. And so for this particular reaction, we looked at these two different pathways. And for our 1,2 adduct, we saw that it has this smaller activation energy barrier. But in terms of the thermodynamics of the reaction, it is not quite as favorable, right? There's that smaller delta G gap. Our 1,4 adduct is the exact opposite. It has a higher activation energy barrier. So it's a slower of the two reactions. But when the reaction does occur, you form a more stable product here. All right? So we call the blue one, our 1,2 adduct in this example, our kinetic product. It's the one that forms the fastest, so that's what's favored at low temperatures. But at high temperatures, our thermodynamic product, the one that's more stable, is the one that's favored. All right? So, well, this is where we kind of left off last time. So let's kind of talk about this a little bit more. All right, so our kinetic product. This is what's going to be favored at low temperatures. Okay? If we look at our free energy diagram here, right, the height of that barrier, that activation energy, we imagine that our reactants are like this little marble over here. And it's trying to jump over that activation energy barrier, right? Well, just how much jumping power it has depends on the temperature of that reaction, right? So a really cold reaction, this thing can't quite get over. The more thermal energy it has, all of a sudden then it can make it over that barrier. So for a cold reaction here, it's going to favor which one of these has the lower activation energy barrier. For a cold, under cold conditions, this thing just does not have enough energy to jump over that higher hurdle, right? So it's going to jump over that little hurdle, and then it's kind of going to get trapped over here, all right? Yes, my product is higher energy than the 1,4, but it's kind of trapped because it just jumped over whatever hurdle was the smaller, all right? So this is the one that's favored at low temperatures. It's the one that forms the fastest. And in terms of our free energy diagram, by forms the fastest, what do I mean with regard to that height of that activation energy barrier? It's bigger, it's small. Small, right? So by forms the fastest, I means it has the smallest activation energy. Okay? In our electrophilic addition of conjugated dienes, this is always the 1,2 adduct. All right, so why is that? This is what they call proximity effect. All right, if we look at our chemical reaction mechanism here, all right, given what we discussed last time, everybody draw in those electron pushing arrows. Draw the first step in this mechanism. All right, that double bond is what plays the role of the nucleophile and attacks that hydrogen. Hydrogen can't have too many bonds, so it's got to give up that pair of electrons to that bromine. All right, and this first step here, it helps explain this proximity effect. So how is that? All right, well, let me draw my intermediate correctly. Now that hydrogen is no longer there, it's now attached over here. Remember that carbocation is going to form always in that allylic position. Okay, well, the bromide ion that forms is right next to that carbocation, right? In order to do the 1,4 addition, we have to have this resonance shift, and then it's got to travel all the way to the other end of our molecule. Well, it would need thermal energy to do that, and since we're at really cold temperatures, it's not moving around very fast at all. So just by where it's automatically located and the fact that it doesn't have a lot of energy to do any traveling, by proximity, it's just going to attach itself to that second position right there. All right? So this proximity effect is quite simply that that bromide ion is located next to that C2 with no energy to travel. All right, so again, our kinetic product will always be the 1,2 adduct, and again, that's because of proximity effect. Okay, our thermodynamic product. This is the one that's favored at high temperatures. All right. It is the one that is the most stable . All right, which in terms of our free energy diagram means the one with the largest negative delta G, right? The largest gap between reactant and product free energy. So most stable, we mean the largest negative delta G. All right, so why is that? Why does higher temperatures give us this more stable product as opposed to the one that forms the fastest? Well, again, if we go back to our little graph here, now my marble's got a ton of energy, right? It can hop over either one of these activation energy barriers freely. Not only that, but once it gets, let's say every once in a while, it will hop over this smaller activation energy barrier here, because that's the product that forms the fastest, but it's got a ton of energy. It can also go back, and then the other way. And basically, it gets to sample all the different possibilities, and it will always choose that lowest energy possibility, right? So because it gets to reach equilibrium, go back and forth, it gets to choose whichever one is going to be the lowest energy. So at high temperatures, where we have plenty of energy to jump over that taller activation energy, our little marble is always going to land at whichever is the lowest energy product, okay? So this is not always the 1,4. It was the 1,4 in our previous example, but it could be either the 1,2 or the 1,4. All right, the key here is whichever one is the most stable. All right, so going back to this example, it was the 1,4. How can I look at these two products and see that this one is the most stable? right? I give you a hint, it has nothing to do with the location of that bromine. The bromine can be on a primary carbon, secondary carbon, doesn't give a crap. All right? What else do we notice about this molecule that corresponds to stability? We talked about this at the very beginning of this chapter. Focusing on the location of that double bond. All right, alkene stability. What are the factors in alkene stability here? Substitution. All right, so let's look. In our 1,2 adduct, what would we call this? Mono-substituted, di-substituted, tri-substituted. This one right here. Remember, we're going to look at our two sp2 hybridized carbons. We're going to count how many carbon neighbors they have. In this case, there's just the one. So this would be a mono-substituted alkene. All right, we said that this was our most stable one, so let's look at its degree of substitution here. I'm going to look at my two sp2 hybridized carbons, and I'm going to count how many neighbors they have. All right, so everybody take a second. Tell me what's the degree of substitution on this one. We got one carbon over here, a second carbon over here, so this one is di-substituted. All right, so how could I tell that this was the most stable? Because I'm going to look at that alkene, that double bond, and I'm going to compare their degrees of substitution. Whichever one is more substituted is going to be more stable and is thus your thermodynamic product. All right, so kinetic product, always 1, 2, boom, right? Because that's the one that's always going to form the fastest. For the thermodynamic product, it's going to be either the 1, 2 or the 1, 4, whichever's more stable. And again, how are we comparing stability? We say whichever one is the more substituted. Oops. All right, cool. So let's do another example here. All right. We're going to react this thing with HBr. All right, and the first thing you're going to do is give me the 1,2 adduct and the 1,4 adduct. Right? What are our two potential products here? All right, so in this case, this molecule is symmetric, so I could count either way. We're going to just label these carbons about our conjugated double bonds. 1, 2, 3, 4. If I want to do my 1, 2 product, I'm going to add the hydrogen to carbon 1 and the bromine to carbon 2. Okay. If I want to do my 1,4 adduct, I'm going to add the hydrogen to carbon 1 and the bromine to carbon 4. All right, but we also made note that when we do our 1,4 adduct, this is what's formed. So first of all, I guess let's just take this step by step. I'm going to add my hydrogen to carbon 1. My bromine is now all the way over here on carbon 4. All right, but remember, in order for this to occur, we had to have this movement of our double bond because of resonance. So our double bond has now moved to be between carbons 2 and 3. All right, so my 1,2 adduct, I put a hydrogen on carbon 1, bromine on carbon 2. My 1,4 adduct, I put my hydrogen on carbon 1, my bromine on carbon 4, and I move that double bond to be between carbons 2 and 3. Okay? So we got our products here. Now let's think, which one is going to be favored at low temperatures? Which one is going to be our kinetic product? 1, 2, and how do we know it's 1, 2? Because it's always 1, 2, right? So this is going to be our kinetic product. All right, and which one's going to be our thermodynamic product? Is it always 1, 4? No, so now we got to go and we got to compare these, and we got to figure out which one is more stable, which one has the higher degree of substitution. All right, so everybody take a second and identify our thermodynamic product. All right, so what's the degree of substitution of the 1, 2? Mono, di, tri, tetra. So this one would be tri-substituted. And what about my substitution of my 1, 4? This is only di-substituted. Right? To be clear, tri-substituted because a 1, 2, 3 carbons bound to those sp2 hybridized carbons. This one's only di-substituted because there's only 1, 2 carbons bound to that sp2 to those sp2 hybridized carbons. So then in this particular example, which one is my thermodynamic product? Also the 1, 2. All right, so this is my thermodynamic product. All right. So this is, in this case, we started with this symmetric diene. So it didn't matter which direction we decided to count from. All right, but how do we deal with an asymmetric diene? All right, and we're specifically going to look at this at low temperatures. But what we're going to find is we have two different 1, 2 adducts. We'll get a different one if I count in this direction. 1, 2, 3, 4. That'll be my blue 1, 2. And we'll get a different 1, 2 if we count in the other direction. 1, 2, 3, 4. So everybody try to take a second and draw me my two 1, 2 products here. right, so if I look at my blue, I'm going to draw my hydrogen on carbon 1 and my bromine on carbon 2. I'm just going to kind of squeeze it in here. Not very accurate bond angles, but that's okay. It's going to drive me nuts. All right. If I wanted to do my 1,2 product, my 1,2 product of the red numbering, I'm going to play the same game, but now with the other double bond. All right, so now over here I have a hydrogen on carbon 1 and my bromine on carbon 2. Okay, so since we had this asymmetric diene, we had to do one where the one double bond, so in this case the blue, that's when this double bond was playing the role of the nucleophile. And then we had to do the other possibility when my red double bond was playing the role of the nucleophile. That's how I got my 2 products here. All right, so which one of these is going to be my major product at low temperatures? Turns out that one is going to be more favorable than the other. Our kinetic product is always the 1,2, so it's definitely going to be one of these two. But I got to think, which one is going to form the fastest? Which one has that smallest activation energy? All right? And in order to determine that, we have to look at let's just ask, which one has the smallest activation energy? All right, well, it's going to be the one with the most stable carbocation. All right, so we got to look at our intermediate here. In the blue one, we had a carbocation on carbon 2 in our blue numbering scheme. On the red one, we had a carbocation on carbon 2 in our red numbering scheme. Both of these are allylic, so they're both super stable from that perspective. All right, but when we're going to break our tie here, now we're going to look at not only are they allylic, so they're tied there, but one of them's more substituted allylic than the other one. Right? So which one of these is going to be the most stable carbocation? The one on the left or the one on the right? The one on the left. So they're both allylic, right? So we can't compare just by that. Check, check. But this one is a tertiary, and this one is only a secondary. All right, so that transition state for this one here will be lower than over here, meaning that this is going to be my major product at low temperatures. All right, if we did the same thing, but we carried this out at high temperatures, we would again have to compare our 1,2 and our 1,4. But now we would have 4 possibilities. And we would draw them all out and compare stability, i.e. which one is more substituted. All right. So for the sake of time, I'm going to leave this to y'all to do. I actually also have a lecture video that I'll post that goes through this again. We kind of got messed up last time with that projector not working, so we're going to move on here to make sure we stay on pace. Okay? But you would have to draw all 4 products and then figure out which one is the most stable, i.e. has the highest degree of substitution. All right, we got one more category of reaction that we're going to cover, which is what's called a Diels-Alder reaction. All right, this is what is called an electrocyclic reaction. Because our electrons move in a circle in our mechanism. All right, this is our conjugated dienes chapter. So we're going to start out with a conjugated diene. I've kind of kinked it into this weird conformation. We'll talk a little bit more about that here in a second. All right, this is actually just 1,2-butadiene. I just rotated it about that central double bond. All right, and so in these Diels-Alder reactions, our diene is going to react with what's called a dienophile. A lover of dienes, which is either going to be an alkene or an alkyne. All right, and in this reaction, the mechanism here are electrons. They move in a circle. All right, there's this circular flow of electrons. All right, this creates a 6-membered ring. All right, so first of all, let's just note, let's sort of trace our carbons here. We have this new 6-membered ring. That's because we had these 4 carbons from our conjugated diene and these 2 carbons from our dienophile. Right? So that's how we got a total of 6 carbons in our new molecule, in our product. Okay? We can see from our electron pushing arrows, this arrow here represents a new sigma bond that's going to be formed. This one over here, our new sigma bond. Right, between my orange and my blue carbon. Likewise, on the other side, here's another formation of a new sigma bond. All right, we got one more to put in here, one more bond, and that's because of this arrow here. This was the movement of a pi bond. So now my pi bond has changed locations to be between carbons 2 and 3 of that conjugated diene. All right, so we see that these 1, 2, 3, 4 carbons of my conjugated diene and these 1, 2 carbons of our dienophile are combined to make this new 6-membered ring. All right, so we got these 2 new sigma bonds that have formed, as well as our pi bond has moved to now be between carbons 2 and 3. All right, so for your Diels-Alder reactions, you are always going to form a 6-membered ring. Right, the 4 sp2 carbons from your diene and the 2 either sp2 or sp if it was an alkyne carbons from your dienophile. And this is the most important thing and the most helpful thing to keep in mind when drawing the products of our Diels-Alder reaction is you better have a new 6-membered ring in there. All right. Personally, I don't find the mechanism to be all that terribly helpful in me figuring out what the products are. Instead, I start with that 6-membered ring and kind of map the carbons from this side over to this side and from over here to over here. Okay? So what do I mean by that? Let's do another example. All right, so if I'm going to draw my product here, I'm going to start by drawing a new 6-membered ring. So I'm like, all right, Diels-Alder reaction, boom, 6-membered ring on the product side. All right. I'm going to label my 4 diene carbons. Okay. I know that these 4, 1, 2, 3, 4 carbons about that conjugated double bond are going to be involved in that reaction. Right? So let's just label these 1, 2, 3, 4. And then we're going to do the same thing on the other side as well. 4 of these carbons, 1, 2, 3, 4, came from that conjugated diene. Okay, we can do the same thing on the other side. We're going to label our 2 dienophile carbons. 1, 2. That means on the other side, these have to be carbons 1 and 2. All right. Now, we're not done yet. We got to map everything else. Right? So if there was a methyl group on carbon 2 on the left, there's got to be a methyl group on the orange carbon 2 on the right. All right, what else do I have to do on the left hand or on the right hand side here? I'm counting carbons. Something's missing here. I have a methyl group on carbon 3 I got to put on there as well. Boom. All right, so we're going to label everything. We're going to map our carbons from our reactants to products. All right, and then there's one more thing that we're forgetting in this product here. The result of that other electron pushing arrow, we have our new sigma bonds here. Check, check, new sigma, new sigma. What was the other arrow for? The movement of that pi bond, right? And that pi bond is always going to move between carbons 2 and 3 of what used to be that diene. So we have a new pi between, in this case, my orange, carbons 2 and 3. Okay, so we're always going to get these 6-membered rings as our products. All right, the easiest way to do this is to just start by drawing a 6-membered ring and then mapping stuff from the left-hand side to the right-hand side, from reactants to products. What's up?
With the movement of the pi bond, does it change the name?
The name?
Yeah, like name, like nomenclature?
Oh, I mean, all of this would definitely have its own unique name compared to over here as well, right? So now this is a 1,2-dimethyl cyclohexene.
Okay.
Yeah, definitely has a completely different name than our two reactants does, yes. All right, so these Diels-Alder reactions, two things to keep in mind here. They will preserve alkene stereochemistry. All right, so what do I mean by that? All right, so first of all, let's just get some practice in. Everybody take a second and draw me my product here. All right, so if I map those 4 carbons from the left and those 2 blue carbons, all right, in order to complete my carbon chain here, what am I going to have to include? I need a methyl group on carbon 1, and what else? Methyl on carbon 4, and my pi bond, right? So now I'm also going to move that pi bond to be between carbons 2 and 3. Okay, cool. Just to sort of get some practice in on drawing these. Okay, but my point here is if we have an alkene that has stereochemistry to it, so now I'm going to add 2 groups on here. Let's put 2 fluorines. Okay, since this is a trans alkene, those 2 fluorines are on opposite sides. When my ring forms, they are also going to be on opposite sides of that ring. So I'm going to draw one in with a wedge and one in with a dash. All right, so a trans alkene will lead to a trans cyclic alkane. Likewise, if we had a cis alkene, it would lead to a cis cyclic alkane because these reactions preserve the stereochemistry of those alkenes. Okay. We said that alkynes can also play the role, of our dienophile. All right, so I'm always going to get that 6-membered ring. Okay, if I map my carbons here, 1, 2, 3, 4. 1, 2. Oops. 1, 2, 3, 4. 1, 2. All right, so first of all, I know I'm going to have to move that pi bond to be between carbons 2 and 3. All right, but in this case, since I started out with an alkyne, one of those pi bonds is going to get consumed in this reaction. The other one isn't. So I'm still going to retain one of those pi bonds between carbons 1 and 2 as well. Okay, so because I started out with an alkyne, an alkyne, we're going to keep one pi bond. Between our blue 1 and 2. All right, so we have these Diels-Alder reactions where we're always forming these 6-membered rings between our conjugated diene and what we call a dienophile. All right, these reactions preserve the stereochemistry of that alkene. And if we have an alkyne dienophile, we're going to keep one of those pi bonds. Cool.